Okay, we'll begin Chapter 6, and the title of Chapter 6 is the Electronic Structure of Atoms. By electronic, we mean how electrons are arranged around atoms. Now, before we can talk about how electrons are arranged, we will have to talk about light. And in fact, the scientists' understanding of electronic arrangement came from first a good understanding of the nature of light and then how light interacts with matter, because it turns out that electrons are the ones that are releasing light. Anytime there's light, whether through a laser or any chemical reaction that produces light, of which there are many, the light comes from electrons. So studying light will give us an understanding of electrons. So real quick, let's talk about light. Classically, light has been thought of as a wave, and a wave has many characteristics. Sound can also be thought of as a wave, and when we say a wave, essentially it's a way to propagate energy. So a sound wave actually is a carrier of energy, and the light wave does exactly the same thing. Any wave has what's called a wavelength, which is simply the distance between the top of one wave, what's called the wave crest, and the top of another wave. And the wavelength for light is actually signified by this little lambda symbol. This is called lambda. This is a Greek symbol. It kind of looks like an upside down Y. We'll be using it throughout this chapter. And for us, it'll be measured in meters. And every wave has a characteristic wavelength, and the wavelength will actually, in our case, determine the light's color. Another characteristic of waves is what's called the amplitude. We're not going to deal too much with amplitude, but the distance, essentially, the height of the wave is the amplitude, and that has to do with how bright the light is. In the case of sound, it would be how loud a certain sound is. The wavelength in sound, for example, would be the pitch, how high or how low the sound is, essentially. So wavelength, for us, is measured in meters. Another, or the second very important characteristic of a wave is something called frequency. Frequency is given by a letter, looks like V, but this is also a Greek letter, and it's kind of written as a cursive V, and it's the Greek letter nu. It's actually pronounced nu, but in our case, we can call it V. And the units are something called Hertz, actually named after a famous scientist, Mr. Hertz, we'll say. And Hertz, what Hertz symbolizes, or what frequency symbolizes, is the number of waves passing a given point per unit of time. So if you take a look at this top wave, what we see 1, 2, 3, 4, 5 crests. So we can say this wave has a frequency of 5. This one we can say has 1, 2 wave crests, if we think of this as coming down here. So the frequency of a wave is how many of these you see in a given second. That's why another way of representing Hertz is per second. Anytime you have a -1 to the power, that actually means per second, or 1 over seconds. And what you can see here is the relationship between frequency and wavelength, and it's an inverse relationship. So the idea is, here in the top wave you have a higher frequency, so therefore you have a lower wavelength. On the bottom wave you have a lower frequency, therefore a higher wavelength. This is called an inverse relationship. And if we were to take this relationship and quantify it, you'll get essentially an equation, which we'll see in a minute. Now, this is what's called the electromagnetic radiation, another word for, a fancy word for light. And only a small fraction, a small slither of this light is actually visible to the human eye. So what we see in the rainbow, from a red, orange, yellow, green, blue, indigo, violet, is actually part of all the light out there. The overwhelming majority of the light we cannot see, but we definitely have technology that's based on a lot of this portion of the light spectrum. In fact, your radio receives its signal from the station in these frequencies out here, your cell phone actually also communicates with its tower and with other cell phones through radio frequencies. Microwaves, we used to cook our food. Infrared, there's a lot of technology based on infrared devices. In fact, your remote communicates with your television through an infrared signal. Ultraviolet, there's plenty of this technology based on this. X-rays, we definitely know about X-rays, being able to see through the flesh of a human down to the bone to see any problems with bones and so forth. And there are some animals that can actually see in the infrared. Notably, the reptiles are able to see in the infrared, just a little bit in the infrared. And there are other animals, birds and the bees, for example, can see in the ultraviolet. Now, we're not going to talk about the birds and the bees in this lecture, simply because we just don't have the time. But what you can see here is you can see the inverse relationship. In fact, you can see the wavelength increasing going to the right. So we have a very short wavelength, 10 to the negative 7, very, very tiny. And then here we have 10 to the negative first, 10 to the first, 10 to the third. 10 to the third number is 1,000 meters, actually. So a kilometer. And then you see frequency increasing this way. So you see a relatively small frequency here and an extremely, extremely high frequency, 10 to the 20th Hertz, which is very, very high. Your visible light, this is important, your visible light is on the order of what's called nanometers. So red will be about 750 nanometers and violet about 400 nanometers. And nano, if you recall, is a billionth of a meter. I think here on the next slide we'll be able to see those conversions if you forgot them. So if we combine frequency and wavelength, we said they are inversely related, and the way to show an inverse relationship in mathematical terms is by multiplying your wavelength and your frequency to give you a constant. In our case, the constant is actually the famous speed of light, which is 3.00 times 10 to the 8th meter per second. So that gives you 300,000 essentially kilometers per second, or in this case 300 million meters per second. So if you were to write this out, 10 to the 8th gives you this many. So you got 300 million meters per second. And if you calculate what light takes in one single second, light can travel roughly 10 times around the Earth in a single second, which gives you an appreciation of how fast, how big this number is and how fast. And this essentially is the speed limit for the universe. Nothing can go faster, at least we think nothing can go faster than the speed of light. So a very important equation here, we're actually going to be dealing with it. Let's quickly review some metric conversions that we will have to use. An important one is kilo, and that's 10 to the third, so 1,000 meters equals 1 kilometer. Some of these are also important for us. The nanometer will be important, which is a billionth of a meter. That's visible light, remember, is on the order of nanometers. A strange one you may not have seen before is something called the angstrom, with this strange letter signifying it. And the reason this is important is because it gives us, an angstrom is 10 to the negative 10th meters. Actually, it uses the base 10 system. It's a perfect base 10 system. And a lot of the distances, intermolecular distances, say between two atoms in a molecule, are on the order of angstroms. So you can say the bond length is 250 angstroms or 50 angstroms, and then the picometer. So make sure you, this is essentially from the summer homework, we had this idea. Make sure you recall it and make sure you can remember these conversions. A new one here though is the angstrom. Okay, why don't we do a little example? And the example, problem 1, says what is the wavelength in millimeters of a wave with a frequency of 550 kilohertz. So your AM stations on your radio are actually, the numbers on the AM station are actually given in kilohertz. So this would be the frequency of an AM station. And if you listen to 550 AM, there's some crazy guys that talk a bunch of nonsense, so tune them in if you haven't yet. Your, by the way, your FM station broadcasts in megahertz. megahertz are 1,000 times bigger than these kilohertz. But we have essentially a wave with this frequency, and we're going to try to get its wavelength. Is kind of the idea. So essentially, the equation we'll be using is the speed of light equals wavelength times frequency. And recall that wavelength, since the speed of light is given in meters per second, 3.00 meters per second, we must ensure that our wavelength is in meters and our frequency is in per second, which is the same thing as, recall, hertz. So we're beginning with a frequency of 500 kilohertz, which means we'll have to first convert into hertz using those prefixes. So on the bottom we'll put kilohertz, on the top we'll put hertz, and just like kilometers and meters, 1 kilometer is 1,000 meters, so 1 kilohertz is 1,000 hertz. And essentially what you get yourself is 500,000 hertz. So this is our frequency. And next we can go ahead and plug this frequency into our equation. And let's first rearrange the equation since we want to solve for wavelength, lambda. Rearrange the equation allows us to say that C divided by nu, or frequency, gives us the wavelength. So let's just plug and chug in this case. Speed of light is 3.00 times 10 to the 8 meters per second divided by 500,000 hertz, and a hertz, I recall, is a meter per second, so I could say per second here, and that will allow our seconds to actually cancel out. So if you plug this into your calculator, that's a good idea to be able to use scientific notation. So 3.0 times 10 to the 8th divided by 500,000, which gives you roughly 600 meters. And if you can see, in this case, the seconds cancel out, so your answer is 600 meters. Now they wanted the answer in millimeters, so then we'll have to convert from meters to millimeters. So we got ourselves 600 meters. We'll convert from meters to millimeters. We call that a millimeter is 1,000th of a meter, so a meter has therefore 1,000 millimeters. Effectively, we're multiplying by 1,000, which gives us 600,000 millimeters. And if we want two significant figures, since we began with, actually I see what I did. I forgot a little 5 in here, did I not? So let's see if we can adjust that. It looks like I forgot the 5. So take a look at this. That should have been a 5, which makes that into a 5. Which makes that into a 5, which changes this completely. So apologize there. So let's try that again. So we got ourselves 3.0 times 10 to the 8th divided by 550. That gives us 545. That works a little better. 545 meters, which then 545 allows us to simply change these. 545. So you get 545,000 millimeters. And for significant figure's sake, let's just say 550,000 millimeters, which coincidentally comes out to be very interestingly close to what we began with. So this would be the frequency, the wavelength of light from the frequency, and we can go vice versa. We can get then frequency given a wavelength. Okay. Light can also be thought of as a particle. So we just looked at light being a wave. Light, famously, there are plenty of experiments performed to demonstrate that light can also be a particle. And a particle, think of it as a tiny little chunk of matter, if you would. And a very famous scientist actually demonstrated this, and that was Mr. Einstein. In fact, Einstein received a Nobel Prize for something called the photoelectric effect, which contributes to a lot of our understanding of solar cells, for example. Today's technology, a lot of the solar cells is based on the photoelectric effect. So through it, what he showed in experiments is that light hitting a metal with a sufficient frequency can actually knock off electrons. Now we definitely know that electrons are matter, and light was able to essentially allow the electrons to be released. And this is essentially what your solar cell is based on. It uses solar light, and it converts that into electricity. Then the electricity can be stored and so forth in a battery. And this particle of light was given a name, and before they got to the name, they gave this definition, something called quanta. Quanta just means a tiny, tiny amount, a set tiny amount. And light is an extremely, extremely small particle, and every particle can be thought of as having an energy. So an energy, and very, very small chunk of energy, will be called a quanta of energy. Max Planck is actually another physicist at this time that was developing the idea with light. So now we have a different equation, one that treats light as a particle, and here's the equation. And because particles have energy, traveling particles have energy, this equation says energy equals h times, this is frequency again, nu, and h in this case is a constant. So if you take a look, the constant is actually a very strange constant, and this constant, called the Planck's constant after a scientist, after Max Planck, is essentially related to the divisibility of nature. This essentially is the smallest possible division. Turns out in nature you can't go and become infinitely small. There's a limit to how small you can get. Kind of strange, but there is a limit, and this essentially is the limit to how small you can get. And it shows up in the understanding of light. So if we know the wavelength of light, we can then calculate the energy of a little chunk of light, a little particle of light, now called a photon, or a little packet, a little quantum of light, is the idea. So this is the second important equation. This equation treats light as a particle. The previous one treated light as a wave. So why don't we do a little calculation where we treat light as a particle. So here it says calculate the quantum of energy that an object can absorb from yellow light whose wavelength is 589 nanometers. So the idea here is we want to be able to find the energy. We want to plug it into this equation, E equals hv, and in order to get your frequency, we'll have to get our frequency from our light as a wave equation, which is C equals lambda v. So if we can get the frequency, we'll just plug the frequency into this equation, and we'll be good to go. We'll find the energy. So let's go ahead and do that first. Rearranging this equation to solve for v gives us v is c over lambda. Speed of light is 3.00 times 10 to the 8 meters per second. In this case, our wavelength was given as 589 nanometers. 589 nanometers. And we will have to convert this to meters, again like we did previously, but because a nanometer, this portion right here is actually times 10 to the negative 9th meters. What you can actually do, that's literally what a nanometer stands for. What you can do is you can actually substitute the little n for times 10 to the negative 9th, and you get yourself 589 times 10 to the negative 9th meters. So I'll actually do that. So this is a quick little handy conversion. So we have 589 times 10 to the negative 9th meters. And if we do this, we'll get ourselves a frequency. So we got 3.0 times 10 to the 8th divided by 589 times 10 to the negative 9th. And what we get is roughly 5.09. Keep a few more significant figures. 093 times 10 to the 14th Hertz, or inverse seconds. And now we're able to plug this value into our E equation, and the energy will be equal, h, recall, is a Planck's constant, so that number will stay the same. So we'll do 6.626 times 10 to the negative 34 joule seconds. And the units for the Planck's constant are joule seconds. Essentially, and it's just so that way we cancel out to give energy in units of joules. And then multiply now by a frequency, which is 5.093 times 10 to the 14th inverse second. So let me go ahead and put inverse per second. That way you'll see our seconds cancel out and we're left with joules. So we'll take that number and multiply it by Planck's constant, 6.626 times 10 to the negative 34. We should get ourselves a value that looks like this, 3.37 times 10 to the negative 19 joules. And using significant figures, it looks like we require 3, so that's exactly what we'll put down. Essentially what this means, if you have yellow light, each little packet of yellow light, so you can think of light again as traveling in particles or as a wave. Remember, light can now be thought of both ways. So each chunk of yellow light has this much energy. And the idea is every different color of light has a different energy value. This is a kind of analogous to how every different atom has a different mass. So every different color of light has a different energy. Think of it that way. If you subdivide light into tiny little chunks called quanta. So there it is, and we'll conclude lesson 1 of chapter 6 here.